Hello, everyone. I'm Peter Mattson. I'm the president of the MLCommons Association and an engineer at Google. And I'm here to talk to you today about MLCommons and the work we're doing with public data sets. So I'm going to give a one-slide summary of the MLCommons Association if you haven't heard of us. MLCommons is a global organization that brings together large companies, small companies, and academics to build the ML ecosystem. Our mission, we like to say, is to make ML better for everyone. And the way we do that is to try and help ML transition from its current state, which in my opinion is kind of like the Wright brothers. We've discovered that we can build planes, and we think they're going to be really, really useful, but we haven't yet figured out how to turn them into the mode of transportation that we all take for granted in every day today. And if we're going to get there, we need a number of things. And we think that the things that we need in the ML ecosystem are summarized by the MLCommons pillars. And those pillars are benchmarks, ways of measuring everything from speed to accuracy, to reliability, to fairness. ML is an incredibly analog field. An ML application works some percentage of the time, and we want to make measurement of things like that as reliable as possible. Data. Public data has created ML as we know it. We wouldn't be here without ImageNet. We want to improve the data that everyone uses to do research, to evaluate new ideas, to drive the field forward. And the last is best practices. Best practices can best be summarized as knowing how to apply ML efficiently and effectively to create value, especially as we see a lot of fields start to try and adopt ML and try and figure out how to make use of it. We'd really like to connect them with the knowledge and capabilities that let them do that. I'm going to deep dive today on this central pillar, data. I believe it really is the central pillar of the field. So why data? Why is it so important? I think it's summed up well by the expression, data is the new code. If you think about this, the best possible functionality of a machine learning application is summed up in the data. It cannot do better than the information, the patterns encoded in the training data you feed the model. Defines the best possible functionality, and the model then, in turn, is effectively a lossy compiler. It translates the information in a training data set into something that you can apply to new data, but you lose some of that along the way. And the goal of model developers is to reduce that loss to be as small as possible. But what they can't do is do any better than the data. If you have bad data, you're going to get bad results. And building data sets is hard, and bad data is a major risk. You have to ask yourself questions like, what data do you have? What data should you acquire to supplement that data? Are there errors in your labels? How do you control costs, such as labeling and compute, and so on? And perhaps most importantly, you need to ask yourself, does your test data sufficiently represent the real-world problem you are trying to solve? This is a critical question. Too often we think, well, we took a piece of our training data, we set that aside, and we tested on that, and it looks good. All that means is that you've managed to represent what was in the training data. It doesn't actually tell you that the training data was good. And if you left out an important use case, like the engineers who designed this bridge did for high winds, and you go to deployment, this is going to come back and bite you. They missed a critical test case. You can do the same in machine learning. Bad training data will produce bad trained models. And if you don't have a good test set, it'll look fine until you deploy it, and then you get bad outcomes. Yet, despite the importance of data, if you look at the literature, you look at the conferences, overwhelmingly, models are the focus of research, while data is often treated as an afterthought. This is slowly beginning to change, but this is still the pattern of the field. If you look at NeurIPS publications by year, they've been increasing exponentially. but only in 2021 did NeurIPS add a track focused on data sets and benchmarking. The fraction of research effort going to what is arguably at least half the value of an ML development is really kind of alarming. So we need to change how we think. We need to figure out how to design data sets. We need to figure out how to create data sets that match our designs. We need to figure out how to measure data quality. Did we do that well? We need to figure out how to evolve our data sets, make them better. And we need to figure out how to make them more efficient. ML does get better the more data you throw at it, but it's climbing an exponential curve. And at some point, that curve becomes prohibitively expensive. And the way that, or one way to deal with that, is to figure out how to use less data to get the same result. And in particular, we need to apply all of these learnings to the public data. Public data sets are essential to the field, and I'll talk a bit more about that in a second. So why are public data sets so important? Because public data sets enable research to do several key things. First of all, they let research attack core technical issues. So there was a time when we didn't know how to build a CNN. And to some extent, the development of data sets like ImageNet gave us an attack surface for overcoming that problem. Okay, so if you have a problem in ML, like say multimodal data, you need a corresponding data set to go after it. They also let us solve impactful problems, things like climate change or cancer diagnosis. You can't go after these problems unless you have appropriate public data sets that frame them for research. Modern ML is built on public data sets. Papers with Code has a great list of the most frequently cited ones. Some research by Vijay Reddy at Harvard showed that public data sets really are the language of ML research. Even at the largest ML-focused companies like Google or Meta, there's still 80% of the usage in research papers. This is how we do experiments and communicate. But ML is evolving. We're rapidly, and for each, exhausting our existing test sets. They pose problems, and more quickly, our ML models overcome those problems, but that doesn't mean that they've solved the real world task that the test sets represent. We also see quality issues in existing data sets. There's some great work by Curtis Northcutt and others on analyzing errors in ImageNet, which we sort of consider the given bedrock of the field. We're seeing a rise of giant models that fine-tune for specific tasks, and this is a new paradigm. Multimodal models are getting more and more important. We're figuring out that there is bias in our existing data, and we'd like to deal with that. And we have increasing legal and ethical concerns about where data comes from. So as the field moves, data sets need to keep pace. We need to ask ourselves, what public data sets will drive research for the next decade? What research challenges, if overcome, benefit everyone, keep us better informed, help us be more productive, make us healthier, make us safer? And given those research challenges, what data sets will the field require? How do we build data sets that include difficult test sets that really model all the nuance of important problems so we can judge how well we're doing? Training sets with higher quality or that work for giant models. How do we correlate multimodal data? How do we reduce the bias in natural language sets, for instance? And how do we do all of this while making sure that the data is legally and ethically sourced? So at MLCommons, we're trying to bring together the industry and folks in academia and figure out how to build public data sets to address these needs. Two of the data sets that we've built that are going to be covered in great detail later in this talk are the People's Speech, which is a very large English speech data set, and multilingual spoken words, which is a keyword data set in over 50 languages. And we'll get to those in more later. We also are focused on figuring out how to build new kinds of data sets to address specific needs. For instance, we have a project called Medperf. The idea of Medperf is to evaluate model quality in healthcare, you really need a diverse patient population, but it can be really hard to get access to medical data for important privacy reasons. So what if instead we took models we wanted to evaluate and sent them to a variety of different medical facilities, evaluated them on small shards of data at each of those facilities, and then composited the results? This would preserve privacy while giving us a much more diverse test set. And this would help ensure that when medical models go out of the lab and into deployment, that they work, which I think is very important for all of us. One of the questions that we ask ourselves is, what tools do we need to create these better data sets? If data is the new code, where are the tools that we take for granted when we work with code? When you think about working with conventional code, you have design documents, standard languages, editors, unit tests, debuggers, profiles, metrics, source control, all of these things. Where are the corresponding tools for data? And I believe we will need this entire stack. There's a lot of work here to be done by everyone involved in the community to advance our ability to code with data. One of the other things that MLCommons in particular is working on to support this tool stack is better metrics. We have a project called Dataperf, which is essentially benchmarks and leaderboards for data. If you think of something like ImageNet as a benchmark for models, you hold the data set constant, you vary the models. It's driven tremendous progress on models. We need similar things for data. We want to measure three things: how good is training data? How accurately does test data reflect all the breadth and difficulty of real-world underlying problems? And how do we build good algorithms for working with both training and test data and making them better? A very simple example of benchmarking training data sets. Basic idea is you hold a set of models constant and you vary the data set. You try and make it better in some way. And then you look at the resulting accuracy on those models when you train them on the improved data set. Test data is almost the reverse. You're looking for data that models can't label, but humans can easily. That is novel. You don't want the same thing over and over. And you're trying to, within that constraint, find the hardest and most diverse data you can. Then you have algorithms that transform a data set. And again, you hold the models constant and you see whether the transformation is a positive one compared to state of the art. We're also beginning to look at source control. How do you enable multiple contributor public data sets? How do you enable multiple people to come in, contribute data? How do you align and verify that? Then how do you drive a continuous improvement loop where you have a design that you're working to, a problem you're trying to solve, and you figure out what data you need and try and get people to contribute it? And then lastly, how do you version and share that with the world so that everyone has access to the data you're creating as a public resource? Our goal is data sets that evolve with ML. They go from research projects trying to figure out what kind of data we might need to research tools to eventually staples of the industry that create a lot of value for everyone, making ML more capable, more reliable, and more ethical. And we think that Dataperf gives us the metrics to measure this progress. And that is tremendously important. ML has the potential to make us healthier, make us safer, give us better access to information, and improve our productivity. And we need all of those things badly. But to do this, we need more smart people, like the folks who will talk about some specific MLCommons data sets shortly. But this is the tip of the iceberg. So please join us. Participate in Dataperf if you have good ideas about how to make data better. Contribute a submission against the benchmarks. Or join us at mlcommons.org. We have lots of working groups working in this area. We'd love to have your idea. Thank you, everyone. And with that, I will hand it over to my collaborators.
I'm Daniel Galvez, and I'll be showing you all today a little bit about the people's speech data set that Peter just brought up to you at the beginning of the talk. This is, at the time we released the data set, it was one of the biggest supervised speech recognition data sets out there that allow commercial usage. There's been quite a lot of changes since then, since we released it in, I think, December 2021. But there's a lot of goodies that I think would be very interesting to show you all. So as a brief agenda, I want to show the motivation of this data set, why we made it, describe the data set, show some training results on the data set. Those are all kind of like typical in these talks, but the one I kind of want to focus on in this talk is data set creation, the actual steps we did in doing that. And the goal isn't to just, tell you every single pipeline step, but something Peter mentioned in his talk is there's a question of what tools we should use for data-centric AI. And so the answers to those questions, you can take an outside view and kind of like make a good guess, just based on thinking about, what size data am I doing? Am I working with? What workloads do I have? But also you kind of discover a few things as you just do the task. And I think, not everyone here is doing speech AI, right? So I think that one will probably be of most interest to the people attending this talk. And at the end, I'll tease a few future work things, just because there's basically no end to this line of work, just being honest. So the basic motivation for the people speech data set was that MLCommons is a benchmarking organization. And if you look at what most companies think of benchmarking, they view it as a commercial activity. So it's a commercial activity because, if you're like a system, like a hardware system or software system seller, people will be making decisions about whether or not to buy or sell, your devices or your systems based on the outcomes of these benchmarks. So in that way, it's commercial usage. One of the challenges you see in a lot of ML is that people might just grab whatever data willy-nilly they want off the internet. And I mean, you can do that, of course, but there's copyright issues that can be implied by that. It's kind of a legal gray zone. There's no ruling, at least in the US specifically, about whether an ML model trained on a copyrighted piece of data is subject to that, the constraints of that copyrighted data. But when it comes to benchmarking, at the very least, companies don't want to take that risk. So they basically want something that has a commercial usage license. And a good way to do that is to accept only public domain and Creative Commons by licensed data. We actually accept Creative Commons by licensed and Creative Commons by SA. I won't get into the details on that, but we separate those out because some companies we spoke to don't like the CC BY SA license. But anyway, generally speaking, you want to limit yourself to public domain and those license types if you want to get wide adoption of your data set. And just a longer term vision, open resources help the ML industry grow, and hopefully I'll get to that later. There's a table down here. It's just comparing the people's speech to a lot of different other data sets at the time when we published the paper on it. You can see they're pretty comparable, but nothing matches big number of hours, diverse speech, and commercial usage, the way that people's speech captures those. I already talked about the license types, but what I want to mention is for this data set, we basically we downloaded 52,500 hours off of archive.org. Archive.org is run by the Internet Archive. And that is basically an American organization whose goal is to basically archive the whole internet. And, some of you have probably seen the Wayback Machine. That's what they do. But they also allow you to just upload, honestly, almost any multimedia onto their website for free. And when you upload, you can specify your license type. And the next slide, I'll show you what that GUI looks like just to give you a sense. But when we discovered this data source, looking into it, we found that most of the data on it is actually fairly interesting. Even though I say 100% English here, it's actually more like 99.9% English, American English specifically. But what you find is local government functions are very common. Things like local city halls, basically, like lot of townships and whatnot in small cities, they might say, we want to, have our city hall talks and whatnot, and local government meetings recorded for people to view, but they're not the most tech savvy. They just kind of want to upload things, and that's that. They upload to archive.org because it's real easy. But you also see things like documentaries, interviews, podcasts, and so on. And that's all pretty novel, I would say, in speech to text. A lot of it for a long time has just been audiobooks and things like TED Talks. That's kind of been the most common thing. The table at the bottom is a breakdown of like different subsets of the data set. That's not important. So just to give a sense, archive.org, if you want to upload data, you're kind of presented with this GUI. I highlighted a box in red towards the bottom, license. Basically, when someone uploads a piece of data, they can select the license. And this all gets indexed by their query engine. So basically, what we can do after the fact is use their API to search for all of the CC BY and CC0 license data. And that's how you do it. That's how you build the data set, I should say. For training results, I have two training results to show you. One is just a very simple model, 20 million parameter CTC loss function. For those of you who know what that is, we get decent results on a common benchmark, WhisperSpeech's dev and test sets. These results are just okay, I would say. They're definitely not like the best results out there. Some of that's due to domain mismatch and whatnot. And also, we only train for 20 V100 hours with this model. But the purpose of this is, if any of you are curious, basically within the span of a day, you can download the data set and train a model on it if you wanted to. That's kind of the purpose of this slide. The actually more interesting results are a much bigger model. So 600 million parameters. To give you a sense, I've seen people training models of up to like 1 billion to 1.5 billion parameters at like the high end of the state of the art. But, 600 million is like very reasonable to see in production these days. Some colleagues at NVIDIA trained a conformer model with a transducer loss head on quite a few data sets. You can click on that link to find out what the data sets are, but basically it's including the people of speech. And I think the total was something like, probably like 60,000 hours went into that data set. And you can see some results on some common benchmarks. Like 1.62% over speech test scoring is basically the best you'll ever get, for example. So the point there is that big data works. And that's another one of the motivations of making something like the people of speech. But before I discuss the dataset creation pipeline and the interesting tools we did for that, this is the most technical slide in the whole talk. And I'm sorry for the wall of text, but there's one little bit I want to talk about first. When we make speech recognition training datasets, you might naively think, oh, okay, you just need to get like audio files and get the transcripts, and the audio files are input and like the transcripts the output, and you train from to map the input to the output. I mean, like that's true, but the problem you find is most objective functions in speech to text, their memory usage grows linearly with the length of the ground truth text and linearly with the length of the audio sequence, and those are multiplied. And that doesn't look quadratic, but it's basically quadratic because T and L are basically linearly associated with each other. So memory usage can go very high if you want to say train on like a whole hour long audio. And we have multiple hours long audio in this in the original input. So we need to chunk that into 15-second chunks in order to get that to work. And there's a question of how you actually do that, because transcripts often tell the text that's being said, but they don't actually say what when it's being said. So we need to like take these correct labels, but then provide correct timestamps. And basically the best way to do this, if you asked anyone who's like done this for a little bit, is to use a pre-trained model to do inference. And that pre-trained model will be able to output timestamps on its predictions. Now, its predictions won't be correct, but the timestamps will be correct on its predictions. And you can basically match the match the incorrect words output by that pre-trained model against the original transcription with like basically any edit distance type dynamic programming thing. Smith-Waterman algorithm is pretty common, but I've definitely seen research where people do more sophisticated things than it. But Smith-Waterman is kind of like the famous one that, everyone does in Algorithms 101 class. So the key takeaway of this whole slide is that supervised speech recognition data set creation is an inference task. And that kind of informs, how we implemented this quickly. So so this is the part that I think is most interesting to all of you. I just want to show some useful artifacts available in the open source code pipeline. So not only is the data set public, but the code to make it is public, which, honestly, I don't know of any other speech recognition data set, at least of this size, that has the code public as well to actually create it. I'm really not sure of anything else. I don't know, maybe someone will email me and tell me, no, you're wrong. But that's like a fairly novel thing. And the cool thing, like the reason why I say artifacts is that you can use these. They're fairly standalone for the most part. And I suspect that they'll be useful to at least some of you. At least some of them will be useful to some people. The first thing is when you download a bunch of data off the internet, duplicates abound. There are a lot of, I'm sure there's like many copies of like the inauguration speech by Obama, for example. It's well known that having duplicates in a training data set degrades the training data set, which is maybe acceptable if you have only a few duplicates, but it's very bad if your test set and your training set overlap, or like they intersect in the set theory sense. So you basically want to remove any overlapping data. And naive methods to do this are quadratic in time. So nearest neighbor search is like the most obvious way to do it. That's big O of n squared, and like that's not that basically just doesn't work. There's some slide where I have the total number of audio documents that we have in here, but I think it's on the order of magnitude of like 10,000 documents to 100,000 documents. And, you square that and then, it's hopeless. So you want to do this in some, at least like linear or linear big O of n or big O of n log n time. Locality sensitive hashing is a very good way to do this. One of the people who worked on the data set, Juan Ciro, he has a paper accepted to the NeurIPS 2021 Data-Centric AI workshop, where he actually discusses how he can use locality sensitive hashing to basically just remove duplicates very easily. And we used his method. Locality sensitive hashing it's been known for a long time, but I think a lot of maybe newer ML practitioners don't know of it because it's not exactly the most ML thing. It kind of showed up in data engineering first. So a lot of people don't know of it, and it's not really taught in schools, but it's very, very effective, especially when you deduplicate text data in particular. Deduplicating multimedia data is harder. It's harder, but I'll get to that at the end. The next thing is, I mentioned that this is an inference task with the pre-trained model. I've worked on a lot of speeding up inference. It's my job at NVIDIA. And what you usually find is you can be very fast at running just the deep learning model on the GPU. But what you end up seeing after that is all your time ends up getting used on the CPU for the beam search. I'm sure lots of people in the audience know what beam search is, but basically it's an important part of inference, and almost everyone runs beam search on the CPU. I'm actually going to have a talk at a future GPU technology conference about this, but you can do beam search on the GPU, and this basically speeds everything up a ton. The reason being is, the reason's Amdahl's law, which I mean, if you know what it is, you know what it is. If you don't, I won't talk about it. But if you look at that pie chart at the bottom, this is referring to a different workload than the actual workload I used, than the actual model and workload that we're talking about in this talk. But basically, it's not uncommon to see, once you GPU accelerate your deep learning model, that language model part, which is 94.7%, that's the beam search decoder. It's very common to see, like, that might be like 95% of the runtime on the CPU. So you need to accelerate that as well. For us, we ended up doing about a 1000x throw times factor. So basically what that meant was, we had 52.5K hours of input data. We were able to process that all and create transcripts from them. Again, these are the approximately correct transcripts, not the ground truth transcripts, but they have timestamps, which we need. We were able to process them in 52.5 hours. So basically 2 days. And that's very game changing, because like, the thing to understand is, like, when you create these data sets, it's an iterative process. You often have to redo things. If you put yourself in a situation where you're like, okay, it takes, N days to do this one step, you won't do that step again. So I would say this is probably one of the most critical parts. So if any of you didn't realize that you can do beam search on the GPU, you can. There's multiple variants of it. Specifically, in this case, is what's called a weighted finite state transducer beam search. The code's open source. You can see the link. I would say it was probably one of the most important pieces to getting this to work. The other thing is, if you look, there's like no standard, there's no standards body like IEEE saying this, but when you download data sets, what format do you see it in? It's a tar file. Sometimes it's a tar gzip. We actually don't use a tar gzip. We use a tar file because gzip does not compress audio data well. That's a common question. Like, most common question I get, they ask, why don't, they're like, this data set's really big, it's 2 terabytes. Why don't you gzip compress it? And the answer is that gzip works on text. It doesn't work on audio. Tar file is the most common thing. So if you want people to use your data set, providing it in a tar file format is very, very, very helpful. Now, if you're using Apache Spark, which a lot of people do, which we used, it doesn't actually support inputting and outputting tar files. So I added support for that. It's not the hardest thing. Java has support for writing tar files, reading them, and so on, but the options are kind of funky. But basically, it's all encapsulated in that file you see there. It's a very small file. I can if the only thing is it's using the Bazel build system, which might be confusing for someone who might just want to copy paste this into their code. But I'm sure I could put it on Maven if someone asked. My contact info is going to be at the end. But yeah, basically what this means is your Apache Spark pipeline can just output tar files at the end. Then you just upload it to whatever hosting server you have, and that's it. Finally, web dataset. Some of you may know of it. It allows you to read tar files directly in PyTorch, as well as TensorFlow. It's a fairly useful library, so you also don't even have to do any processing of the tar files either. This is what NVIDIA NeMo does, for example. Their de facto format is actually using tar files. So it's fairly robust and allows you to train high throughput models. So this is one of the more interesting tools, situations you'll find. Basically, Hugging Face, if you want to upload Hugging Face, you need to use Git, and you need to use Git LFS, large file storage. Git add is a serial operation. It goes over each file one at a time. And Git add, adding something to the index is actually fairly fast normally, because you're just adding text files, code files. When you do Git add on a giant binary blob that is going to be handled by Git LFS, it actually does a SHA-256 hash on the whole thing. Now, when you have to SHA-256 hash 2 terabytes of data serially, this actually takes a long time. When I say a long time, I think it took a whole day to upload to Hugging Face when we first did this, and we're like, what's going on? And then we found out what was going on. This strace-p is a very useful tool, everybody. But now, like we got it down to like about an hour just by effectively using Git's plumbing commands to call git LFS clean, which does that SHA-256 hash to compute the hashes in advance, and then simply running git hash object with those specific flags details to make that work. We actually don't have code to share for this, annoyingly. It's still kind of being worked out a little bit, but if anyone's ever uploading a huge data set to Hugging Face, point them this way. If they're like, why is it so slow? I think we can skip this one, but if any of you ever want to download data off archive.org, the query syntax is a little bit confusing, but we do have an example available that you can see. Like, that's how we download our original source data, and anyone can use it. It's an Apache 2 license. The whole code base is Apache 2 licensed. Now, finally, I just want to tease a few interesting things in the future. This is not part of the people speech, but these are things to think about for generate big data. One is that many people say that the future of ML is unsupervised, and a lot of people just say this, but I just want to provide a statistic to give you a sense of why that may be the case. So we had 52.5K hours total of source data for supervised people speech, but if you look at all of the appropriate license data that could be used, it's actually 581K hours. So it's basically a 10x increase. So, 11x, I suppose, but that's basically why people say that, the future is unsupervised, because there's just at least an order of magnitude more data. Another thing is going on the unsupervised train. I mentioned briefly that, locality sensitive hashing is very good on text data, but how do we deduplicate on-labeled video and audio data? I have a few hunches how this may work, but I don't think there's a generally accepted solution today, the way there is that locality sensitive hashing just always works for text deduplication. So I'd say it's also something which needs to be solved if you want to build a very big unsupervised data set. Finally, multilingual. Multilingual, if you look at this, there's surprisingly, it surprised me how few non-English audio there was on archive.org when we looked into this. I did look at Common Crawl. They actually have surprisingly fewer web video text tracks in the most recent dump. Web video text track is a transcript format in the most recent dump than I would have expected. My hunch is that Common Crawl would have, a lot of non-English data, but I don't quite know. So, 76,000, we use 76K files from archive.org to create people speak, but there's only apparently 12.5K files on Common Crawl. Something that seems odd about that to me. So I think someone needs to investigate that and ask the question of why are there so few? It's possible that Common Crawl may just avoid crawling sites with a lot of video and audio data. Maybe they just don't have the inbound bandwidth to do that, or maybe those websites kind of block them from doing that. I don't know, but that definitely strikes me as a bit of a puzzle. Anyway, if you want to get started with the people speech data set, you can download it at that URL on Hugging Face, but you probably just Google Hugging Face people speech. The data creation pipeline is open source. If you just want to see the main thing, there it is. Finally, there's a tutorial about how to use NVIDIA and email to train on it that I also mentioned at the beginning. You can take a look there. And finally, thank you. If any of you want to contact me, my contact email is right there. Always happy to answer questions. And if anyone's interested in this, definitely feel free to send me a message.
Hi everyone, I'm Mark Mazumder, a PhD candidate at Harvard University in Professor Vijay Janapur Reddy's lab, and today I'll be presenting the multilingual spoken words corpus, a data set of spoken words in 50 languages which can be used for developing voice interface and keyword search applications. This data set is an effort I led in collaboration with Daniel Galvez, Peter Mattson, and a large team of folks at Harvard and across industry in collaboration with MLCommons. We published our work last year in the Dataset and Benchmarks track in Europe's. Let's start with a brief overview of current challenges in keyword spotting datasets. Voice interaction has become ubiquitous. But the wake words that are used to trigger activation with these interfaces still only support very limited vocabularies in only a few languages. So you're familiar with things like OK followed by Google and Hey followed by Siri, but what do you do when you want another keyword? Well, a traditional keyword spotting model requires thousands to millions of training examples per keyword, and this is prohibitively difficult to collect. So our goal is to make voice interfaces available to a worldwide audience and reduce this burdensome data requirement. In particular, keyword spotting is usually just the beginning of a job that launches and runs in the cloud. But for many interactions, is this really necessary? For many tasks, a microcontroller running a keyword spotting model would be enough, but the real challenge is in having enough training data to support the right keyword in the language that you want. Our dataset is a first step towards this goal. Most publicly available keyword datasets only contain a handful of keywords, and most keyword spotting data is in English. Our dataset, the multilingual spoken words corpus, greatly expands on the scope of available keyword spotting data for research and commercial use. And in particular, the reason we built this dataset is shown on the image on the left. This shows the population of native speakers by language, where each circle represents the size of the population. Most speech training data is found in English, but English native speakers are just a portion of the potential audience for voice interfaces. And in general, there's very little training data available in the long tail, where most native speakers are actually found. Providing accurate general speech recognition, though, for all of these languages is still too resource intensive. Instead, we think that small vocabulary speech recognition is a solvable task right now, and we can democratize voice interfaces for all languages. In particular, keyword spotting models can fit on these tiny microcontrollers that only cost a few dollars, opening the door to adding voice interaction to almost anything you can think of. So now let's look at what's in the dataset. We've roughly categorized our dataset into 3 buckets. Depending on the number of hours we have in each language, you can see we have low, medium, and high resource categories. For the languages in the low resource category, we have less than 10 hours of data each, whereas for the medium and high resource categories, we have significantly more. However, for many of these languages, this represents the first keyword spotting dataset that's publicly available. And in terms of reach, these languages are estimated to be natively spoken in total by over 5 billion people, representing a significant potential reach. To provide a bit more detail, you can see that for low-resource languages, we have on average around 500 keywords and around 10,000 samples, whereas on the high end, each language has around 23,000 keywords with a total of nearly 2 million recorded instances in each language. In aggregate, the dataset contains over 340,000 keywords, 23 million audio samples, and this comprises over 6,000 hours of data. What kind of words do we contain in our dataset? Our code also includes some off-the-shelf NLP tools to allow a user to perform some rough keyword characterization for many of the languages in our dataset, even if they don't speak the language. This includes estimated parts of speech tagging, as well as semantic inference, such as which keywords refer to locations, technology, culture, etc. Our hope is that this shortens the time to market for any prototype voice interface. Depending on what task you're performing, you can search for what the dataset provides and whether it's a good fit for your application. And users can prototype an interface solution in one language and potentially get a working prototype in a dozen other languages with minimal additional effort. We provide pre-computed splits to allow for comparative evaluation, and we try to optimize for gender balance and minimal speaker overlap across splits to the best extent possible. Now we'll switch to describing how we built the dataset from existing crowdsourced data and how our pipeline for automated keyword dataset generation can be extended to new sources of data. This is the general pipeline, where we start with dataset ingestion, keyword extraction, and finally filtering. The idea here is that we want to be able to support a wide variety of inputs because there's a lot of speech data out there. But in particular, when you perform naive keyword extraction, you might end up with a large, noisy keyword dataset. So we also provide some data filtering tools so that a user can decide what the right balance is for them in order to get a smaller, cleaner keyword spotting dataset. For our initial release, we source our data from Common Voice, a massive crowdsourced speech dataset which contains over 93 languages and provides sentence, audio, and text transcription pairs. Our dataset is comprised of extracted keywords from Common Voice sentences. These keywords can then be used to directly train keyword spotting models or used as pre-training data to potentially support any keyword in any language as described in our paper. Let's briefly walk through the steps of our dataset generation pipeline. We begin by taking input pairs of text transcription and sentence audio. And then we run forced alignment, a well-established technique in speech processing, in order to estimate the timings of each word boundary. We use the Montreal Forced Aligner to perform forced alignment, and our alignments are trained from a flat start. In other words, we don't require any prior acoustic model for each language. Next, we use these estimated word boundaries to extract each keyword, but in this case we have some keyword inclusion criteria. First, we look for a minimum character length of 3, or 2 for Chinese, just to act as a coarse stop word filter, so we're not including words like a, an, of, to. This is because it's hard to get precise forced alignment word boundaries for these kinds of stop words, and those words tend to not be useful in keyword spotting tasks. We also require a minimum of 5 samples per keyword. Once we've extracted each keyword into our dataset, then we can train keyword spotting models. You might ask, what's the difference between extracted keywords and intentionally individually recorded keyword samples? In particular, is there an accuracy gap between models trained with one type of data versus the other? We investigated this by comparing our dataset to Google Speech Commands, which is a gold standard in keyword spotting research. This dataset provides 35 keywords and over 105,000 verified recording samples. We hold fixed a common keyword spotting model architecture and train 2 models, one using our data and another using Google Speech Commands data. We then evaluate both models on the test split of Google Speech Commands and observe an accuracy gap smaller than 7%. We think that this indicates that our dataset is ready to be used for prototyping purposes for a wide variety of keyword spotting tasks. Our dataset will be maintained and updated by MLCommons, including additional languages and words over time. The dataset is free to download, easy to import, and it's licensed both for commercial and academic use. To maximize our impact, we make both our data and code easily accessible. In particular, we include an introductory Colab tutorial for getting started with our dataset. This tutorial allows you to listen to samples, compare against Google Speech Commands, train few-shot keyword spotting models, and visualize embeddings. We hope you'll check out our dataset, and thank you very much for your time.